Hi, my name is Zhang. I'm with Group 4, and my project, or our experiment, was experiment number 5 on the Rankine cycle. So this next slide is just a quick outline of what I'm going to talk about, going through the introduction briefly, the apparatus, the data, the equations that was used, and then talk about the results, and also the uncertainty analysis, and then wrap it up. So this first picture is just a simplified diagram of the Rankine cycle. We have our major components there for the pump, to the steam generator, which is our boiler, into the turbine, and into the condenser, and then loops back around. This next slide is the ideal cycle on the PV and the TS chart. From 1 to 2 is the pump, where we have the water to get into our boiler. And from the boiler, we have 2 to 3, which is just adding energy until we preferably get out of the liquid vapor dome, so it's superheated. And then from 3 to 4, we have the condenser, so we condense it back down to liquid. And from 4 to 1, from 3 to 4 is a turbine, where we extract the pressure to mechanical energy, which and then turns our turbine to power our generator. And then from 4 to 1, we have the condenser, which condenses it back to water, and then the cycle just starts over again. So here's our apparatus. It's in the back, the Rankine cycler steam turbine power system. Just briefly run through the procedure. We had a startup procedure to warm it up. We first added the water, and we warm it up until we get to 110 psi, and then we shut it back down. Then we started our steady state, and at that point we used the control valve for the steam emission valve to control the pressure at 110 psi. And then we also use this knob right here for the load rheostat to keep the load at 0.2 amps and 6 volts. So next, here are just two of the graph that I created using Excel, using the data. It's the turbine inlet and exit pressure versus time, and the turbine inlet and exit temperature versus time. Those are just two I put up. There's appendices. Here are the data collected from the time I picked in our steady state, which is 70.314 seconds into it. It's a little over a minute into it. Here's all the data. We have atmospheric pressure at 2.7. Our initial boiler fill amount was 5,500 milliliters. The fuel flow for the light propane was 0.00553 meter cube per minute, and the rest going just really quick. So from this data, we use these key equations to calculate the power out, power in, the efficiencies, and electrical power that was generated. So the first set of calculation was done for the boiler. We have the heat provided by the light propane tank, which was calculated using the heat of combustion of light propane times the fuel flow, which we got from the DAC unit from the Rankine cycler. And then the heat out is just the enthalpy times the mass flow rate. And then we got the efficiencies of the boiler, which is around 11.1045%, which is, I guess, expected. So as you can see from the cycle for the boiler is 2 to 3. And ideally we want the boiler to, I guess, heat up the water until we get out of the liquid vapor dome to superheated, so we keep our turbine happy because we don't want any water vapor in our turbine. There was an issue with this because the point I picked, the temperature was like slightly off. I was using a program to interpolate all the data, and it was saying that it was like less than 0.5 degrees Celsius. Like it was short of being superheated. I just kind of rounded up because it was so small of a number. Then for the turbine, we have the from 3 to 4, so we get the enthalpy at 3 and 4 due to, I guess, difference, and multiply that by the mass flow rate, we get about 7 watts. But the actual work rate, which was the current times the voltage, we only got 1.098 watts, and the efficiency was around 15.49%, which that's decent for what we have. And then we have the condenser, we have the heat flow out, which is we got the information from state 4, and we assumed state 1 since we didn't really have anything from the pump being recorded in our DAC unit. So we just kind of went for state 2. We assumed that entropy was constant. We found, like, using the, I guess, the fact that we know that it's a liquid, saturated liquid, and the fact that it has the same entropy as 2, we were able to find the enthalpy there, and we calculated the efficiency for that. And then for the, that was weird. It was supposed to show all the boilers, the turbine inlet, turbine outlet, condenser inlet, and condenser outlet. I don't know why it's showing up like that. I can't really fix it, but it's supposed to list all the pressures, the temperature, the specific volume, the enthalpy, the internal energy, and entropy for all these the states in the system. I don't know why it's showing up like that. So with all that data listed, we were able to calculate the thermal efficiency of the whole system, which is around 5.6%. From what the group lead had, they were like around 1 to 2%. And I guess some of our calculations might have been off. I guess some of our assumptions might have been off. Also, there's uncertainty values that I'll get to next. So, but overall, it was somewhat expected. Just a little bit on the high side. Then you also got to take into account the ideal versus real life. It's not going to exactly follow the ideal cycle that I presented earlier. And then here's some uncertainty analysis. Most of the uncertainty came from the resolution that was being displayed from the DAC unit, which is it's 1/2 of the resolution. I didn't really see any data spec sheets on Moodle for our equipment, so I wasn't able to calculate any of the other uncertainties to get the design uncertainties. But that's what I have for all those. It all went to the 0.001 place, so divided by half, I got 0.005 for almost all the data. And then also this standard deviation and mean calculation for all the points we were given. Again, if you remember earlier from the graphs I showed, the pressure wasn't as steady, the temperature wasn't as steady. I just picked, for the time I picked, it was just the most steady time around then. But from all those unsteady times, we were able to calculate the standard deviation and mean values for all the data we got from the DAC unit. So some possible sources of errors, and I guess the conclusion to wrap this up is like we have some human errors. We might not have kept the valves exactly at 110 psi, or the load exactly at 0.2 or 0.2 amps and 6 volts. And some of the assumptions like that, we had to make assumptions to make some of these numbers make sense. Again, like the boiler, the outlet wasn't really hot enough to be superheated vapor by like 0.3 degrees Celsius. Some of the uncertainty values could have played in the fact that we got some weird numbers. But overall, the number came out to what we kind of expected. And wrapping up, this is the sources, the thermal book, the steam table, from the thermal book, the lab manual, the handbook that we were able to find online. Also, here's the appendices, like I said, the other data or graphs I made. Again, you see here, the temperature was steady around here and then it just shot up for some reason. And it was mostly steady, like for the other ones. Like right here, it seems like it was more steady around I guess the first few minutes, like 2 or 3 minutes. That's where I got my data from. That's it. Good question.